Hello, thank you for joining me for this short talk on parasitic coefficient modeling and shielding effectiveness in electronic enclosures. Ideally, the behavior of an electronic circuit would be determined by only the properties of its components, but there are stray effects that come into play, particularly related to capacitance and inductance. And these will cause unwanted interactions that may be important in your device. So in this webinar, we'll be exploring what these phenomena are and ways that we can model them. Integrated engineering software has been around since 1984. We've been providing electromagnetic and thermal simulation software. In general, our software is used for purposes such as reducing prototyping and gaining insight into how devices work by modeling how the fields are actually generated and what kinds of fields, forces, and other interactions exist. Virtual prototyping is, of course, faster and less expensive than physical prototyping. It doesn't replace physical prototyping, but it certainly reduces the amount of it. In circuit design, you would normally be using, among other tools, something like I show here. KASP is a program that Integrated represents in North America. In Asia, there will be other distributors for it. It's one of many power electronic simulation tools out there, but for me it's a convenient way of depicting a tool that would let you put together components, wire them up, specify their properties, and then run a simulation. From our perspective, what our company does as its main business, we're not focused on the components. What we're focused on is all these line traces, which are not necessarily drawn literally in the circuit. They're just wires connecting parts to parts and electrodes to electrodes, but they represent a physical connection. So what we will be interested in is something more like what I depict in the lower part of the left-hand screen, representing a small part of the circuit that was shown in KASP. If these wires were in fact very close to the physical representation, it might look something like is shown in the lower picture here, with these lines coming out this way being represented by something like a bridge going over top of a line, and lines that have branching or nodal points in between where they connect the different components of the board. So what we're interested in doing is studying field and inductance, capacitance types of effects related to these lines. So in an integrated model, one would draw it as shown previously, but one would also generally make associations and nice labels as depicted here, so that one could clearly see in your physical model that you construct what the interpretation of different parts is, and especially as we start solving and getting answers that are going to be numbered according to the corresponding line parts, a labeled colored diagram like this can be quite handy, and we'll refer back to it a few times. So we'll provide some simple examples here to demonstrate electric field modeling, capacitance modeling, which is related to the electric effects, but skipping over the details of the field, and then similarly magnetic field modeling and inductance and partial inductance modeling. So the first thing that we're going to do is to give you a little bit of a sense of the software itself. This is our 3D electric field modeling software known as Coulomb, one of the first programs that we had released it back around 1986. Of course, it's developed a lot in that time. And what you're looking at here for the case of the circuit board that we've been discussing is a very typical kind of solution. What we've done here, if we look at the physics, is that we've assigned in purple a voltage. In this case, I put 5 volts on for the purple. The blue represents where I've indicated a fixed ground, and the blue represents lines that are conductive, so they will achieve a uniform voltage, but they have been isolated by very high resistance values so that they're not being forced to any particular voltage value. So they will simply float to whatever voltage they float to. And so if we return to the contour plot that I was showing initially, then you will see that indeed if we look around any one of these, here's the 5 volts around this strip line. This one is achieving a kind of blue-green color around the 1.7 volt range, and so on. They have all floated to different values, this one being much closer to, let's say, 1 volt. On the right-hand side, I have a logarithmic scale graph showing the electric field as we move away from the device. So understanding how the voltages actually divide on the circuit board and how some of your floating lines in particular might float to a particular voltage value is one of the things that you can do with electric field analysis. Another thing you can do is look very directly at issues related to interference. So if I zoom out here and I mouse over this curve, then you can see a blue marker moving along the curve, which is telling me how strong the field is at the given location. So we have a correspondence shown with this line. Let me increase the size of these labels a little bit because they're not very readable right now. So I have in fact plotted on a logarithmic scale which has gone from about 200 right beside the board to about 0.3 20 centimeters away. So the electric field decays by a factor of approximately 1,000 as we move away from the board. And on a relative scale you can see the line here as we move away. So we can study at great distances from the board and see the potential for electric fields that might violate some criteria, such as some regulatory rule that you need to abide by. We can see that very easily because this was solved with a boundary element solution. And the boundary elements is generally the fastest and most accurate way to solve something like this. But by far the most commonly known solution of this type is finite elements. So for comparison, I'm just going to do a live solution of this model with finite elements. I've switched the type to finite elements, I hit Run Solver, and it's going to proceed and create the outputs that I had automatically defined. So we've done a very fast, simple simulation here. And if I pull up the output manager and take a look at the second step, then we see that the voltage contours look the same whether I'm looking at step 1 or step 2. Very small shifts there. If I spent more time refining the solution, they would look really identical. So the difference between the two doesn't show up that much right on the circuit board, but if we look at the 2D graphs, look at the finite element solution, you can see that it does follow somewhat the boundary element solution as we move away here, but it suddenly cuts off. And the reason is inherent to the finite element method. It cuts off right here. The finite element method forces you to draw an artificial box around your model and solve in that. So here is the boundary of our box. Let me go to a translucent view and show you that once we get to the boundary of the box, the solution drops off to nothing because it can't model outside that box. So finite elements works on some artificially bounded space where boundary elements only needs to mesh the actual geometry and can therefore predict the fields anywhere automatically. One doesn't have to mess around with boundaries and mesh gradients in order to get good results far away. So that's the only time I'm going to spend on live demo here because it is going to be somewhat time consuming to do so. So here is another example going back to just running boundary elements from here on of an actual board will normally be encased in some type of compartment. And in this case, I've drawn just a rectangular metal box with a couple of large holes in it. And you will usually not have a perfectly sealed metal box around. And again, for regulatory types of issues, how strong is the field some distance away? How much might it be affecting something else? So you can see from the curves here, which are following the same line, once I've put the metal case on, I've dropped down by another factor of somewhere around 30 or so at the far away distances. So the field far away is much less because of the case. You can also see that it's affected the voltage distribution right on the board surface substantially. Having that ground means that the whole board is much closer to 0 volts except right beside where I've assigned the 5 volts. So a way to understand this more completely, the kind of onboard interactions that's subject to different kinds of geometry, will be to look at this not as a fields problem, in which case you need to keep assigning one thing and then another and examining what you've got, but to look at it as a capacitance problem. I've labeled here, using the same numbers as I gave the lines in the model, 1 to 6, the different lines, all of which may in general be at different voltages. And this means that by the pure definition of capacitance, capacitance 1,1 means if I put 1 volt on conductor 1, this is the charge that will appear on that conductor. If I put 1 volt on capacitor 1, C12 is the charge that will appear on conductor 2, and so on. So if I compare what the program gave me, here I've output the capacitance matrix. It computes to a text file so that I get a nice matrix display of it. And I'm showing beside or underneath that, I'm showing the results of sequentially putting 1 volt on this one and all the others at 0, 1 volt on this one and all the others at 0, and so on, sequentially stepwise this way. And you see the charge that's on these completely matches the capacitance result. So that's what your capacitance matrix lets you do, is to see at a glance how much effect each pair of conductors has on each other. You may, if you're familiar with capacitance matrices, be expecting this to be symmetric. In the case of no ground connections anywhere, where all the charge on one conductor has to appear on another because there's nowhere else for charge to go, your matrix will be symmetric. But we have solved this in a grounded simulation, meaning that somewhere out there, there is a real world ground that will in general hold a little bit of the charge. That's what makes the voltage decay to zero as you move far away. And because of that, the matrix will not be quite symmetric. The two solutions did mesh the model a little bit different, so if you look enough decimal places, then you will see some small differences. So the capacitance matrix then gives me a way of understanding what we saw in the voltage plot very nicely. If I look at it with and without the metal case, we can see that the diagonal here, the self-effects, there's actually a little bit higher capacitance for all of these conductors once I put the metal case in. So the self-capacitance of every line is actually a little bit higher when you put on the metal case. That means if you wanted to draw these parasitic effects right into your circuit model, you would put a capacitor of this value between this line and a ground somewhere. And if you wanted to include, let's say, C12, you would put a capacitor of this value between this line and line 2, line 1 and line 2, and so on. What you can see is that the metal case has caused all of the self-effects to become a little bit higher, because the self-capacitance is the capacitance relative to ground. We've brought it closer. Rather than being a vague, far-away world that's at zero, I've brought 0 volts closer. So, of course, the interaction is stronger. But for the off-diagonal elements, you can see that in all cases, the metal case has lowered it, in some cases very dramatically. Number 6 here, from e to the minus 15 to the e to the minus 19. In other cases, less dramatically, from 3.4 to 2.0 e to the minus 14. But in all cases, bringing the metal case closer means that the surroundings are more affected by the ground and as a result, less affected by their immediate neighbors. So one can more broadly describe that as bringing metals, any big pieces of metal such as a copper sheet or case parts close to the board will affect these mutual and self capacitances that exist. The same thing will happen in magnetic modeling. So let's examine a magnetic solution here. In the electric mode, each line was thought of as a single entity. We put a voltage on it, or we didn't, and said it will float to some voltage, but it was in and of itself a single entity. But in magnetic mode, we don't have it so easy, because magnetic effects relate to how the current flows through the line. We have small voltage differences across the line that cause current to flow, but depending how things are switched on and off at all of the connection points, you'll get different current flows. So in the case of line number 3 here, which has an inverted T type of junction, if this was left kind of floating, not at any voltage because of a very high impedance, that would mean no current flows up this way, and therefore all the current flowed in a simple L shape like this, shown to the right. Likewise, you might have no current flowing out this way. It would flow in more of a C shape, or if there's no current in this part of the branch, then we get current flowing like this. So all of these possibilities, the 3 that are shown individually there, are of course superposable. They're kind of a base set, so the general current solution will be some combination of these. So there's a lot more mess here because what I draw as one part actually has contributions from 3 different ways the current might be running through it. So similar to electric modeling, we can solve in either a circuit parameters mode or we can solve in a fields mode. And here I've shown a combination of plots that are a little messy, but give the idea that you can generally explore visually how putting currents into these generates magnetic fields in the vicinity. So I've put 1 amp running down, as mentioned here, in the L-shaped configuration, so running like this in a kind of backwards L in the direction we're looking at it. And I represent the field visually a couple of ways. If you're looking just on a plane and only interested in the magnitude, then contour plots can be nice. And I made this contour plot have a silver type of color scale so that it was visually distinct from the colored arrows that I put surrounding it. It's easy to see color-wise which is which. So you can see here that the magnetic field has a high value of about 1 millitesla right beside the line, and that decays. Again, I've used a logarithmic scale because we span a very wide range. I don't want to just have a little bit of white right beside the line and then black everywhere else. So I use a log scale, and you can see it decaying off by orders of magnitude as we go here. So it's dropped by about a factor of 300 from 1e to the -3 to 3e to the -6 by the time we're looking at the scale on the outer edges here. So the magnetic effects are very local, but again, one wants to be sure for regulatory issues, and one may want to study this in isolation with different types of boxes, pieces of like ground sheets around and all that kind of thing if field values in the vicinity are of interest. But looking at the arrow plot here, I'm simply depicting the direction and magnitude of the field in some region of space above the circuit board. And you can see from this that the direction of the field is this kind of loop. I haven't shown it underneath, but it loops around. Magnetic fields wrap around the lines that are carrying current. The key thing as far as mutual interactions go is that because the magnetic field is reaching over to the other lines, there's going to be a magnetic field on them, and therefore as the current changes, there's going to be an oscillating magnetic field on those. And an oscillating magnetic field will cause an electric field, which will cause current flow in those ones. So if we express this more mathematically, the curl of the electric field that's generated is equal to the time derivative of the magnetic field at any spot. So this would be very messy to study point by point. But the fortunate thing is that this all becomes very nicely modeled by working with what's known as the inductance. The inductance says, look at the total magnetic flux that goes through a loop, that's known as the flux linkage, and work with a proportionality ratio. We say that the mutual inductance between any coil and any other coil is the flux linkage flowing in one coil due to the current flowing in another coil. So in the case of an inductor that you would use in a circuit, that's one coil. There only is L11, so we don't bother saying 1,1. We usually just call the inductance. There only is one coil. But in general, inductance is a matrix. Every potential current path has some inductance between every other potential current path. So again, if we do a fields mode comparison, here is a result table showing if I put 1 amp in the top loop and then look at the flux linkage in the two coils, then put 1 amp in the bottom loop and look at the flux linkage in the two coils. And then I solve in circuit parameters mode and see the inductance reported, you see that they're the same thing. Which is as it should be. It's satisfying the definition. So we can really look at it either way, but rather than having to manually put current in and out of different coils, the inductance mode lets us simply pull it all off in one shot. So one problem with what I've shown there is that your circuit board doesn't have closed loops. Ultimately it does, because current only flows when there is a closed loop. But those closed loops depend a lot as you open and close different resistance values associated with different components of the circuit. Your current is going to follow different paths. So studying all of those different paths and trying to make a physical model of them is really not very friendly. So what's a practical way to look at this? A practical way is to look at something called the partial inductance. And that is the inductance due to just a single part of it. And this forces you, with our software, to use the circuit parameters mode, because in fields mode you can only work out inductance by getting flux linkage. So where you have no closed path, you have no flux linkage. So let's illustrate a little bit by simply taking out a section of the top coil. If we take that out and look at the inductance here, we see 3.17 e to the minus 7 for the self term. Now if we model only the missing part for the top coil, that was 1.04 e to the minus 7. Add those together and you get 4.21. And we see that the inductance calculated for that in the full model is 4.27. So it's only off by about 1%. It's a very good approximation to the self-inductance to do that. But the self-inductance isn't necessarily even what we're interested in. If you want to say, when I run current through one part of the circuit, am I going to see some unwanted current flowing in another part of the circuit? For that, you really want to look at the mutual inductance. So the self-inductance includes terms that don't add up nicely together like this, but the mutual inductance, it actually works out exactly here. If you look at these decimal places, 7.81 e to the minus 9, add that to 2.233 e to the minus 8, and you will in fact get 3.013 e to the minus 8. So the partial inductance is a practical way of getting the results that we need here, because it lets us look at things and say, okay, I might, as I open and close things, generate this loop. I have a partial inductance for this compared to this loop, and I have a partial inductance for this compared to this loop. I'll just add them together to get what would be the total case. Or if I want to say, I might put in this part, or I might put in this part, an elbow, I can look at the self-inductance or the mutual inductance, partial inductance due to both of those, and I can swap it into the calculation. I can take one out, put the other one in. If you do the math across here, like I did for the first case, you'll see that the same things still hold true. So as I've got different possibilities that I might put on, each of these partial inductances say, how much does this part of the circuit affect some other part of the circuit, as seen by the inductance types of calculations. So again, if you get an inductance that's big enough for kind of the frequencies and voltages and so on that you're working with, then you might want to draw that mutual term right into your circuit diagram for modeling purposes to model in your circuit simulator what's going to happen. So if we look at our actual circuit board here rather than the generic two loops, you can see that these values are small in this sample case, and in general they will be small. When you measure, let's say, an inductance with a multimeter, you put probes across, you don't really worry about the inductance of your wires. And if you tried to measure the inductance of these, your wires probably have more inductance in the part that you're measuring. So these are small in general, but again, depending on your frequency and so on, they may add up to a significant effect. So if you want to model them, this is the recommended way to do it with our magnetic software. So with a half-hour presentation like this, we can only really begin to show all the analysis possibilities. We haven't even touched on high-frequency analysis here or eddy currents, but we hope that this presentation has been useful to you and has maybe piqued your interest in looking at our software if this type of analysis looks like you should be doing it. So thank you for attending, and please contact us if you have any questions.